Hello, welcome back to three-phase circuits, Wye-Wye problems. We have an interesting problem on the board that goes as follows. We know the magnitude of the phase voltage of a Y-connected source. We're given that as 240 volts. Notice we're only given that the magnitude of that guy. The line impedance is given by 0.2 plus J1.6 ohms per phase. The balance load, this tells you it's a balanced circuit, has an impedance of 23.8 plus J 5.4 ohms per phase. The phase sequence is ABC. That tells you it's a positive phase sequence. And this is a little cryptic, but the A phase, that's what this is telling you, the A phase is the reference. Okay. Now what we have to do here is find all of the line currents, find all of the line voltages at the source, find all of the phase voltages at the source, and find all the line voltages at the load. So basically we're trying to find the line currents, the line voltages, the phase voltage, and the line voltages at the source and at the load. So it's actually a lot because for each one of these, for instance, the line voltages at the source, there's going to be three answers, A, B, and C. But now you know we essentially draw a three-phase circuit. We find everything for A, and then to find B and C, we just subtract and add 120, and we know the phase sequence here is positive, so we know how to do that. So again, these problems typically don't give you a circuit. So you're going to have to draw a circuit, and what I always recommend, and I still have my sketch over here, is to have a sketch of a full three-phase circuit over there to reference. But step one, even though it's not listed here, is to draw your three-phase equivalent circuit. So that's what we're going to do first, and that's going to make it easier to understand what they're actually asking you to do. If you don't do a single-phase equivalent circuit, of course you can still find the answer, but it's just harder to mentally get there, to figure out what to do. All right, so we have, in our A phase, we have some source, okay? And we go up here to draw a source impedance, right? But then we read our problem, and our problem doesn't have any information about a source impedance at all. So a lot of these problems are going to require you to make assumptions along the way. You know, in the last problem we made some assumptions on phase angles and phase sequences. In this problem we're going to have to make some assumptions. If they don't give you any information at all about a source impedance, then you would just need to make an assumption, because if you just put an arbitrary impedance here, you're not going to be able to solve the problem. You need to make some assumption. So I'm going to assume that this impedance is 0. I'm going to assume this is a perfect source, just like any other problem in circuits from way back when. You don't assume that there's any impedance with the source unless you're told otherwise. So here is that, and then we have terminal little a. I'll draw it in a second. We have some line impedance. It's a resistor and an inductor, and we have some load impedance, which is a resistor and again another inductor. And I'll draw a little line here, I'll draw a little line here, and I'll connect them here. I know that line isn't too straight, but you get my meaning here. So let's go for the low-hanging fruit first. First of all, this line impedance is given to us. The line impedance, where is it at here, is 0.2 plus J1.6. So 0.2 ohms, J1.6 ohms. So that's easy. And then we say the load impedance is 23.8 J 5.4. So 23.8 ohms, J 5.4 ohms. And then we go to the next low-hanging fruit. We label this little a, capital A. And this is little n for little neutral, capital N for capital neutral. And then we start labeling our voltages here. Let's do this color here. We don't have to, you don't have to do this, but I like to do it. I like to go ahead and draw this as V capital A-N, because it just helps me remember what it actually is. And then this is V cap lowercase a-n. I guess I kind of did that wrong, but anyway, you see it's the voltage between those 2 points. Now the only thing that's really left in the drawing that I didn't draw is the voltage of the source. So we go back to the problem and see what we can find. The magnitude of the phase voltage of a Y-connected source. That's what it's telling you, the phase voltage. When you see the term phase voltage, it means here you have a phase. We call it a single phase equivalent circuit. It's the phase voltage, the voltage from across that phase through that part. So what it's telling you is the magnitude of the phase voltage across the source is 240. So from here, this is the phase through the source down to neutral. That's 240 volts. So I'm going to write it as 240. And then you keep reading. It doesn't give you any magnitude information, but then you keep reading and it says the A phase is the reference. So what it means is some voltage across in this reference somewhere in the A phase needs to be the reference. If you really wanted to, you could choose VAN to be 0 degrees. That's what, when they say that it's the reference, they're saying that it's 0 degrees. Everything else is relative to it. It's not going to change anything because all the voltages and currents in the circuit, they're all going to be what they're going to be, and they're just